Good morning, everybody. My name is Alejandro, and today I will discuss DAPCy, which is an efficient Python package for efficient population structure analysis using multivariable techniques. So to begin, I would like to present the concept of population structure, which refers to genetic relatedness among subgroups within species. This is a fundamental process in aspect in population genetic studies since it helps to uncover genetic relatedness with genetic subgroups within samples, and it helps to understand or to describe genetic ancestry, the demography, or even its implications in genome-wide association studies. So several methods and measurements exist, but the most common approaches are based on dimensionality reduction techniques or multivariable methods. So one of the most popular methods in population genetics, population structure analysis, is the discriminant analysis of principal components, or DAPCy method, which combines principal component analysis and linear discriminant analysis to describe between group and within group components using the genotype matrix. The DAPCy method is efficient in estimating these genetic groups because it doesn't assume any genetic processes such as linkage disequilibrium patterns or Hardy-Weinberg equilibrium. For this method, it is necessary to have information on the samples, but if the information is not available, researchers can go for a de novo clustering analysis using k-means clusters on the principal components. Currently, the DAPCy method is only available in R with the package ADGenet. But on its current implementation, the DAPCy method has challenges on analyzing large data sets because its algorithm is based on computing the principal components based on the full rank singular value discomposition. And for model performance, cross-validation is performed with bootstrapping, which for large genomic data set can deal to low runtime and biases on the predictions. In addition, for genomic data sets derived from genotyping arrays or sequencing technologies such as whole genome, whole exome, or even long-read sequencing, it can be computationally prohibitive. So for this, to address this limitation, we developed DAPCy, which is a Python implementation of the DAPCy method using the machine learning framework of Python, which is scikit-learn. Here, as main features, DAPCy uses the genotype data and converts it into a compressed bar representation and estimates the principal components using a truncated singular value discomposition, which instead of going a full rank discomposition, it only calculates the top k components to enhance speed and scalability across large genomic datasets. In addition, for cross-validation, we implement automated cross-validation using a k-fold or stratified k-fold with grid search for hyperparameter tuning. And since it was developed as a scikit-learn machine learning model, it can be used as a classifier, as a portable classifier for new samples when there is no, for example, a cluster or a big infrastructure for this kind of analysis. And so for this presentation, we use these datasets to evaluate the capabilities of DAPCy. Here we use two datasets, the Plasmodium falciparum PF7 dataset from the Malaria Genomic Network, which includes 20,000 partized samples from 33 countries, and the 1,000 Genome Project, which includes over 2,000 samples from 26 countries covering continental population. But before explaining the application to the datasets, I will explain the DAPCy. So as I mentioned, DAPCy was developed as a scikit-learn machine learning model. Here, DAPCy reads genomic data in format of BCF files or PLIN formats and transfers the genotype values into a compressed bar representation. So the DAPCy method and the k-means clustering are designed as a machine learning modules, and also DAPCy, beyond that, offers visualization and reporting functions to observe the genetic clusters and also to assess the model performance of the DAPCy method. So the DAPCy method, as I mentioned, the DAPCy method is implemented as a machine learning instance in which users can create a new instance of the model and specifies a number of principal components to test. For evaluation, the DAPCy offers automated functions to assess the accuracy of the DAPCy method and select based on a cross-validation scheme. So with the obtained results, then users can either visualize the PCA plots or the LDA plots from the DAPCy outcomes. For hyperparameter tuning, then DAPCy implements automatic grid search where users can specify a range of principal components and also the cross-validation scheme, either k-fold or stratified k-fold for imbalanced class labels. For grid search, the grid search also uses multi-threading for evaluating multiple hyperparameters for fast analysis. In addition, after the optimal number of principal components with a high accuracy is obtained, then users can automatically update the instance of the DAPCy model and use it as a classifier for new samples. Similarly, as the DAPCy model, the k-means cluster is also implemented a machine learning class in which users can specify the number of principal components, also with the number of genetic clusters to test. For evaluation schemes, DAPCy offers the ELMO method and silhouette scores to help users to determine the optimal number of clusters based on the principal components. Once that the optimal cluster is obtained, then users can predict the new data labels and then integrate it into the DAPCy model for population structure analysis. So now using the two datasets, the PF7 and the 1000 genome project dataset, we first evaluated DAPCy, computational runtime and memory efficiency. So here in the left plot, we can see that DAPCy is able to fit both datasets at different sample sizes and with a maximum number of 120 principal components. And we can see that it doesn't use most of RAM usage. The memory usage doesn't exceed 10 gigabytes of RAM. In addition, at different principal components, DAPCy computational runtime and DAPCy did increase sharply. And here we can see that for the PF7 dataset, it took seconds, while for the 1000 genome project, which consists of over 300,000 quality control SNPs, it only takes minutes. We also benchmark DAPCy with the R implementation of the DAPCy method using the PF7 dataset. And here in the right plot, using the cross-validation schemes and up to 120 principal components, we can see that DAPCy is 14 times faster than the DAPCy method. And here, in the plot below, we can see that for DAPCy provides high accurate and robust estimates compared to the DAPCy method which cross-validation relies on bootstrapping. So now we perform a population structure analysis with for the PF7 dataset, and we can see that DAPCy was able to identify with an optimal number of 32 principal components and accuracy over 70%. We see that DAPCy identified two main clusters. One main cluster including the samples from Asia and Oceania, and one main cluster including the samples from South America and African samples. And here we can see that DAPCy also identified two main subclusters differentiating between the West African and African samples. I have to apologize for the labels because issues with my presentation slides. But finally, for the 1000 genome project, we see that DAPCy, that using an optimal number of 25 principal components with an accuracy of over 73%, DAPCy is able to identify the main genetic groups based on continental populations. And here we can see that DAPCy, from the samples identified from East Asian samples, South Asian, one cluster for the European and American samples also suggests an admixture, and African samples. And here we can see that this Results are similar from the previous studies on the 1000 genome project, which uses principal component analysis based on the eigenstruct method for genome-wide association studies. So to finish, DAPCy and documentation is freely available at GitLab, PyPad, and Bioconda. We encourage the community to use, explore, and also to contribute to this fact to DAPCy, enhancing the use of population structure analysis of population studies for large-scale datasets. Thank you very much for questions. I'm open for questions.
Time for questions.
Yes, and which type of input data in this package use?
Sorry?
Which type of input data this package use?
The input data here will be a BCFR variant called 5 with all the SNAPE's annotation and also the PLIN format or BET file, which includes the binary format of the genotype values.
Yeah, I have one. The result of the 1000 genome project was a bit surprising to see East Asian population very far from the other ones. I'm not sure if that's exactly the same outcome of the original project. So my question will be, if you make validation, you have a gold standard set of, let's say, assigned populations, and you have done accuracy compared to a gold standard of...
No, here the difference between the results of this one or the previous one or the 1000 genome project is because the DAPCy method calculates the principal components directly with the genotype data, while the ones from the previous 1000 genome project studies is because they use a principal component based on the genetic relationship matrix. So here, this is two different approaches that describe the same thing. Because in the one of the genome-wide association studies, he's standardizing the allele frequencies, while the DAPCy method, it doesn't do anything. That's the reason why it's a popular method, because based on the characteristics of the PCA and LDA, it doesn't assume any genetic assumption.
All right, that is good, but that's beautiful, but okay. Any more questions? All right, then let's start the speaker again.